My name is Justin. I'm a senior principal engineer at Dell. A lot of you guys might be wondering, like, why is Dell even here? What do we care about OpenXT? We actually do a lot of work on TXT, TPM, Secure Boot. OpenXT is one of the best users of all of those things combined. We really want to make sure that all those things work together really, really well. We also sell a lot of systems to government, downstream projects like SecureView. We want to keep selling those systems, make sure that our customers who use those projects are really having the best experience. I'm going to talk today, kind of walk you through what we do to create our static root of trust, dynamic root of trust, and then talk a little bit about SMM, how are we protecting SMM, and how can you trust that SMM is actually doing what it says it's supposed to do. So you guys know what BIOS does. Basically, we get the hardware ready to run the bootloader. That includes configuring things like SMM and locking down the SMM configuration. And we'll get to that later. Because BIOS executes before the rest of the operating system, there's not a lot of operating system protections in place. So we want to make sure that we protect the BIOS itself from being overwritten. And we do that in the chipset, in the hardware, with basically 3 registers. The first is the sometimes called write protect disable, also called BIOS write enable. When this bit is cleared, the CPU has no write access to the SPI flash part. The second bit is the BIOS lock enable bit. This bit will actually trigger an SMI, a system management interrupt, if the write protect disable bit is changed from a 0 to a 1. So if you have some malicious code and it tries to set the write protect disable to 1, it wants to write to the flash part, the SMI will be triggered and a SMI handler will actually turn that back off. So to the attacker, it looks like there's no, the write just didn't even work. Yes?
This is specific to a relatively recent Intel PCH?
This was taken from PCH like Gen 9, so it's not new.
I guess it seems useful to try to express what the scope is. Like these registers are specific to certain Intel.
Oh yeah, this particular implementation, yes, is specific to Intel and it moves around on different chipsets. So yeah, thanks. The third one is SMM BIOS write protect. This actually sort of a catch-all. If we forget to configure the other 2, this bit will actually prevent any write to the flash part from outside of SMM. Second thing we want to do is sometimes we want to update the BIOS itself, security fixes, new features. So we actually follow NIST 800-147 for signing our updates. When we have a BIOS update, we will sign it with Dell's private key, push that down to the platform, and in SMM we will verify the signature before writing it out to flash. These 2 things kind of worked pretty well for a while. Operating systems were widely vulnerable. There weren't a lot of people focused on attacking firmware. Then operating systems got a lot better and people said, hey, here's this thing that runs before the operating system. How can we get in there? And this protection scheme, this one and the SMM write protect, really tie the security of the BIOS to the security of SMM. And so as SMM has kind of grown, the attack surface has gotten really, really large. So in order to continue to protect the flash, we've actually implemented on Intel, it's called BIOSGuard, where there's a hardware-assisted write protection. So each write to the flash part is digitally signed. And if we zoom in on that update package from Dell, you see that we actually split it up. And each one of these slices is a set of instructions on how to flash it, erase this region, write this data to this region of flash. And each one of those set of instructions is signed again with Dell's private key. So BIOSGuard actually has control of the flash write enable in the PCH, and you can have your flash part split up into protected and unprotected regions. So what we do is we protect the code regions, but things like UEFI variables need to be written at runtime. So these are unprotected regions. When you are writing to an unprotected region, you still need to sign. You still need to send the write through this BIOSGuard process. So that signature can be created on the fly or can be pre-scripted, but it's not tied to a specific private key set in the factory. That's great, but when you buy your system from Dell, how do you trust what's actually already on the flash? So this is where you have a static root of trust, and we'll kind of walk through each stage of the BIOS and build it up, starting with hardware reset. When you first come out of hardware reset, the CPU will execute a little bit of ROM code to find and load the ACM. It also makes a measurement of that ACM into PCR0. This is the core root of trust for measurement. The BootGuard ACM will actually then verify the first stage of BIOS. BIOS is split up into multiple stages. BootGuard can't verify the full BIOS image, so we split it up and we take just the first little bit, whatever the limit is. That first stage of BIOS is then responsible for verifying the rest of BIOS. And so before execution, we take a measurement and we compare to a predetermined measurement and trust the next stage. Once BIOS is ready to boot the bootloader, run the bootloader, that's where UEFI Secure Boot comes into play, where we have a trust store of certificates and we verify the OS bootloader. So looking at BootGuard, BootGuard actually has a number of different profiles, but it mainly boils down to measured boot and verified boot. So measured boot, as we've said before, will just simply measure the boot block, push that measurement to the PCR0, and then just continue executing. Verified boot actually fuses the hash of the public key into the PCH and will prevent execution of the boot block if the signature does not match. So Dell, we fuse that hash in our factory, and we will actually not boot any firmware that's not signed by the Dell private key. Because we control the hardware, we control the supply chain management, it's our stance that with the current implementation of BootGuard, this is the most secure method for our customers. Once BootGuard is able to verify the boot block, we are able to take a measurement of the second stage of BIOS and compare it to a measurement that we made when we actually compiled the BIOS. We took that hash and inserted it into the boot block before we signed it, and then there's some code in the boot block that will actually measure and compare the hash at runtime. Again, if the hash doesn't match, we'll block execution or enter a recovery mode so that you could recover your system if it had been tampered with. UEFI Secure Boot, I'm not going to talk too much about it. There's a lot of documentation about it, but in Dell's default configuration, we include the Microsoft third-party UEFI CA certificate. This is what the EFI shim bootloader is signed with. Option ROMs, like from NVIDIA, are signed with this. This is how we're able to trust code that wasn't written by Dell and was added to the system from a third party. Customers are able to enroll their own keys. They can use audit mode, which was defined in UEFI 2.6, to actually add their key to the system and check the results before deploying it. So if you put your key in and you forgot to sign your bootloader, you won't be prevented from booting until you actually deploy the key in deployed mode. So if we add it all together, you see that each stage, right, is measuring and executing the next stage. The measurements are put into the TPM all along the way. I want to talk real quick about some of the measurements that we put into the PCRs. I've seen some variations. We're fully compliant with the TCG specification, but there's a couple things that are maybe open to interpretation. The PCR0 is where the BIOS code is measured. It's your core root of trust measurement. The BootGuard ACM, we don't really do anything special there. Just we measure the BIOS code. PCR1 is where we put the BIOS configuration. So that's static SM BIOS structures, things that describe the physical hardware of your system, what's in what PCI slots, that sort of thing, things that aren't expected to change. User configurable setup options also. So if you go into BIOS setup and you enable the UEFI network stack, that's measured into PCR1 as well. PCR2, we measure option ROM code, but we actually only measure option ROM code from add-in devices. So on a notebook, if we have a NVIDIA graphics card, but the option ROM is embedded into the BIOS and stored on SPI Flash, that's actually measured in PCR0. So if you, same thing on desktops. So if you add in a video card, but you're still using the internal graphics as your default graphics during BIOS, we only execute the internal option ROM. So you wouldn't see any change in PCR2. The rest of them are all defined by the TCG platform specification. Those are just a couple differences. That's great. The static root of trust in a perfect world would be amazing. That's all we would need. But there's sometimes some issues with it. You have to trust all the code that's executed from the very beginning. And if you come up to a system and you want to reset that trust boundary, you have to completely reset the system. Again, any change to any configuration, even something that might be an expected configuration change, will still result in a different PCR measurement. So it can be difficult to maintain a static root of trust across a lot of different devices. So that's where we have the dynamic root of trust, right? On Intel, TXT lets you reset the trust of the platform. You reset PCRs 17 through 22, clear them to a known state, and the TXT SINIT is actually able to measure just the ACM and then any MLE you might have after that. Again, the ACM is protected with a signature, so you have this verified boot continuing forward. That works great, again, in theory, but we have this little thing, SMM, hanging out on the side. SMM, right, is this privileged mode. The system can be interrupted and firmware code can be run at any time, even interrupting your hypervisor or your operating system. So how do we protect SMM? I'm going to go through kind of a few different classes of vulnerabilities that we've seen, how we protect against them, and how we might continue to protect against them in the future. The first and simplest one is actually just executing code from outside the protected SMRAM region. So during boot, we configure this SMRAM. We lock it down so it's invisible to the operating system. Nobody can insert code in there. That's where all our SMI handlers are stored. When you get an SMI, we'll start executing the SMI handler. If the SMI handler intentionally or unintentionally starts executing code from outside of SMRAM, that could be attacker-controlled code and really could break the trust of your system. What we've done in modern chipsets is we actually enable a CPU protection that will trigger a machine check exception if we execute outside of SMRAM. So the CPU will actually halt execution, and we won't allow the attacker code to be executed. Some other things that we could do is taking like OS execution protections and actually implementing them within SMRAM. That's not done today, but like it could be in the future. Another class is the confused deputy, where you have some SMI handler that's supposed to write out some data out to an application. It used to be that the buffer, the output buffer, was actually dynamically allocated and passed into the SMI handler in a CPU register. That works good, it seems to work in just the happy path. The SMI handler will write the data out to the user allocated buffer, but an attacker could change that buffer to point to some kernel memory, or maybe the SM base address, and take over control of SMRAM. So what do? We actually get rid of this dynamically allocated buffer just as a concept. Instead, we use a fixed address that we set during boot, and the SMI handler will only write to that address. And so any calling application is responsible for using that address. We'll check before we actually write the data out that we're writing into that targeted address that we chose at boot. Even if we do use a fixed COM buffer, you still can be vulnerable to DMA attacks. This would commonly look like if you have this fixed COM buffer and your requested data size is in that buffer. So your application first puts in how much data it wants, and then the SMI handler would check, oh, is that bigger than the buffer size that we know? No, okay, just go ahead and copy it. But if a DMA were to come in the middle of that and actually change the passed in buffer after the check, but before we actually do the copy, you could easily overflow the buffer. So to prevent that from happening, we actually will copy that first D word. We'll actually copy the input parameter into SMRAM, where DMA can't touch it. DMA can't write into tseg. And then we'll just operate on that copied in value before writing out to the buffer again. Some other DMA attacks that could be used, you could attack the static root of trust. We take these measurements very early in the boot process. There is an opportunity for a DMA engine to actually modify the code in memory before it's executed. We actually block all DMA until SMRAM is locked. In order to protect that integrity of SMRAM, we want to make sure that no external code's executed. We do the same thing with option ROMs. Until SMRAM is locked, no third-party code from off-chip can actually be executed. We also disable DMA, or we provide the option to disable DMA from Thunderbolt during post. So you can't have a casual passerby plug in a malicious DMA device and break the security of your system. Possible that we could also enable IOMMU during pre-boot environment to actually isolate those devices. Again, not something that we do today, but it's definitely a possibility. Okay, I saved the bad words for the end. Microsoft has, I don't want to step all over Microsoft's toes, but they've kind of hinted that they're adding a lot of virtualization-based technology. A lot of the same things that OpenXT has included for a long time are finally making their way into Windows, really becoming more mainstream. Things like TXT, SMM mitigations. We really continue to see OpenXT as valuable, really pushing the boundary, pushing the envelope, but it's nice to see that there will be some broader adoption of these technologies throughout the industry. And I included a link here to a really great talk from Microsoft talking about all the different things that they're including and how firmware contributes to that too. So what I want you guys to take away is that even though we have these really great OS protections, we have dynamic root of trust, it really also builds on the static root of trust. You can't have one without the other because of SMM. You kind of really need to trust but verify your firmware implementation. So taking stock of your static root of trust measurements is really important for OS security. That's it. Anybody have any questions? Yeah.
A lot of these platform features depend on the manageability in terms of the functions.
Yeah.
How much investment have you made in auditing or reviewing or breaking or something to gain assurance that it's
It's a great question. He asked, a lot of these technologies are rooted in the Intel ME. And as we've seen, that's not always the best idea.
Never.
We are at an Intel office, so
That's a place to say it.
yeah. We are looking at other ways to implement static root of trust that doesn't rely on the ME, but I can't say too much about where we're going with that. I saw another hand over here.
You said we should trust but verify. How do we verify your closed source firmware?
I don't have an answer to that.
Could you publish your measurements?
Yes, we actually do. I can show you how to get them. They are available. Yeah, they are publicly available, so I can show you how to get to them.
Thank you for your presentation, especially the beginning of the presentation. As I understand correctly, it is not possible to install any different BIOS, for example, code on your card today.
It's not, because we implement verified boot and we're tied to the Dell private key.
Okay.
Yeah.
What is it? What is the source code base for UEFI implementation? Do you use either Tianoco or something like that?
Yeah, the question was, what's the code base that we use? Our code base is EDK2 and Tianocore, yeah. Go ahead.
In the measurement chain slide, you showed SEC measuring PEI, measuring Dixie, measuring BDS. Are those just measurements, or is that a signature?
So that's not exactly how it's done. It's kind of it shows you each stage individually, but in reality, we have SEC and PEI are made as one measurement, and verification right as part of BootGuard, and then the rest of BIOS is done as a verification and measurement as well.
So it's independently signed, and you have PEI code that's got a public key baked in.
We have the measurement of that second stage embedded in the boot block, so it's not a signature. The boot block is signed right. We're just extending the trust based on the measurement. Right. Yeah. Go ahead.
Those of us who are not willing to live without verifying your bids, what can Dell do to help us put our own alternative in there, like any?
Because of the way that BootGuard verified boot works, we don't have a way to do that right now because we have our private key, right? It's only going to run Dell firmware for now. Yeah, I understand. We would like to do more, but given the kind of two modes of BootGuard, that's how we can do it.
Is that fair to take away, though, that you feel constrained by the functionality that BootGuard offers, and that if there was something higher fidelity available, that you'd be open to having more flexibility in the firmware?
It's something we would investigate. I mean, it's not, I can't commit to doing it right, but the idea that most customers aren't going to replace their firmware means that we're going to do what's best for the vast majority of our customers. So,
Why can't you provide a verifiable BIOS?
a verifiable in what way?
So, following on question, why can't we see the source?
I don't have an answer to that. Most of it is open source. Most of it is based on EDK2.
Who should we ask? Like, what's the escalation chain with Dell?
I can certainly take that back from this conference. I mean, that's valuable feedback for us to know that people want to look at it. Certainly, it's no secret we're in an open source kind of community here, right? Yeah, it's something that I personally think would be a good idea, but I have to push it up.
Does anyone not care? So you can say unanimously.
Yeah, absolutely.
What kind of critical mass would you need to just purely verify, so that, for instance, the major secure boot proposal that I had would be for the custom firmwares?
Yeah, I don't know that there's any one number of people requesting it, right? It's really a business decision also. We want to protect our interest and make sure that we're not opening ourselves to any kind of attacks, especially compared to other OEMs. We don't want to be the most vulnerable notebook. So, yes.
Are there any plans in the future for an STM?
I didn't cover STM, you're right, but I haven't seen a lot of work around it.
Used to be.
Yeah, I haven't seen anything very recently.
I know there's talks later on about it, but
Yeah,
there's no any one system that actually has one.
right.
So we talk a lot about it, but
Yeah,
until one's actually in a system, it's kind of pointless.
yeah. Yeah.
I'll do one more.
Well, wait for the next guy.
Do you have custom Dell stuff in system management mode beyond the hardening of existing functionality that you described? Like, or do you guys explicitly exert back pressure against like no new stuff?
We're working a lot to reduce. There was kind of this big growth, right? Of, oh, hey, we got this SMM thing. We can put a lot of features and a lot of Dell sauce in there, right? And we're trying to back away from that because it kind of got unmanageable and really, oh, now we have to keep track of all these different mitigations.
Back all the way away? What if SMM is gone?
I don't think so, because a lot of our manageability features rely on having some runtime firmware interaction.
On all products or just servers?
I'm in client, actually, so I can't speak to server.
I'll let you be in peace.
Yeah.
So when a BootGuard vulnerability is discovered, do you have any anti-rollback provisions?
Yeah, so there is a secure version that can be incremented so that it's fused into the CPU. Once you move up, you can't go back.
And where is that verified? Is that
I believe it's in the ACM, but I'm not positive. Yeah. All right. Thank you, guys.